Hey y'all, this is my video lab presentation on the fourth lab, which is on oscillations. For this lab, we're expected to use two fundamental principles, Newton's second law and the energy principle, to study the physics of an oscillating spring mass system. For starters, we are expected to use tracker to analyze the motion of the moving mass. Here is the video. As you can see from the graph, that the motion is like a sinusoidal wave, where it oscillates between one point and the other. With these position and time data, we're able to calculate the period of oscillation, the length of the unstretched spring, and the spring stiffness or the spring constant. That would help us to calculate the energies that will be present in the spring mass system later. So, first off, here's the Python program which I wrote for this lab. Using Newton's second law, we have to predict the new velocity as well as the new position of the spring mass system. So, here is the thing running. As you can see, the spring is oscillating in two dimensions, where the x component is into the computer screen and the y component is to the right of the screen. So this follows the motion of the spring mass system, as seen by the sinusoidal wave. After predicting the motion, we're expected to use the second fundamental principle, the energy principle, which states that the total sum of energy transfers within a system and its surroundings is equal to all the individual energy changes, which refers to kinetic energy, the spring potential energy as the spring stretches and compresses, and the gravitational potential energy since the mass is hung above the ground. So by combining the total sum of these energies, we'll get delta E, which refers to the total amount of energy. Using this graph, we're able to see that the energy changes fluctuate as the spring moves along. As the spring is released from rest, the blue line, which represents kinetic energy, immediately increases, as we can see that the spring mass system moves, so kinetic energy is increasing. On the other hand, we can see that the green line, which represents gravitational potential energy, starts to decrease as the distance from the ground to this mass is shortened as the spring mass system moves nearer and nearer to the ground. Or as some might put it, some of the gravitational energy has been converted into kinetic energy. From here we can also see that the spring potential energy also changes. It dips down for the first part of the motion of the spring mass system. This also shows through as the spring is slightly stretched, so some of the energy is dissipated. However, when the spring reaches one of its oscillation points, the total amount of kinetic energy decreases down to a minimum, whereas the amount of spring potential energy increases and the amount of gravitational potential energy increases, as now more potential energy is stored and is ready to be transferred again back into kinetic energy. From this graph, we can see that the total amount of energy decreases over time. This shows that the energy principle may not hold true, because we're still lacking in one form of energy, thermal energy, where it accounts for the air resistance as well as the friction of the spring with the attachment point. So the total amount of energy will decrease over time due to this energy loss. By using this yellow line, which refers to the total sum of energy, delta E, we can see that the energy principle does not seem to be abided as small fluctuations appear in the graph. However, I can dare say that the energy principle is fulfilled to a small extent only in the first part of the movement when delta T is small. So this concludes my lab presentation on the oscillation motion of a spring mass system.